Today it's our pleasure to have Shane Davis from CITA. Shane did his graduate work at the University of Santa Barbara, followed by a stint as a postdoc at the IIS, and now he's been here at CITA for almost 4 years. And today he's going to tell us about radiation feedback in ultraluminous infrared galaxies. So I'd like to thank the Visitors Committee for inviting me. And note it's been 8 years since my last CITA seminar, so I think it's about time. And hopefully we'll get some more CITA people to give talks, because I think there's some free time in the schedule. So if people are interested, let us know. I think for some reason no one wants to come to Toronto in February or March. So. Okay, so as the title implies, I'm going to be talking about photons and how they interact with matter. And so this title is aimed at the question of whether or not and how photons interact with the gas around them in star-forming galaxies. And so the talk is going to be fairly heavily centered on numerics, and so I'll do some explaining of our recent simulation results. So my collaborators in this are Jan-Fei Jiang, who's a postdoc at the CFA, Jim Stone, who's a professor at Princeton, and most of you guys know Norm. So the simulations I'm going to be showing were done using our radiation hydrodynamics code, which was developed by Jan-Fei, myself, and Jim. And Norm's been a useful person to bounce ideas off and chat with. So the outline, just to give you an idea of where I'm going with this, I'm going to start off with some observational and theoretical motivations for why we think radiation feedback is important, particularly in these star-forming galaxies. I'll give you a description of our radiation transfer method, our numerical simulation techniques, and which I should note we've implemented in the Athena astrophysical code. And then I'll give a short sort of description of some tests and applications before moving on to the main application, the focus of this talk, which is the effect of Rayleigh-Taylor instability in these star-forming galaxies, specifically how this instability works when you have a dusty atmosphere. Okay, start with motivation. So I'm talking about star-forming galaxies, and what I mean by a star-forming galaxy is pretty much any galaxy that's forming stars at a rate that's fairly rapid given its size. So to give you a sense, the star formation rate for the galaxy is roughly a solar mass per year. So we might be talking about dwarf galaxies, which are relatively small, that are forming stars at maybe 3 to 10 solar masses per year, so-called starburst galaxies, or things like ultraluminous infrared galaxies, which are quite a bit bigger and can be forming stars up to hundreds of solar masses per year. And there's even things at high redshift that are inferred to have star formation rates of thousands of solar masses per year, although those are somewhat tentative, I think. So what's somewhat ubiquitous about these sources is they all show these large-scale outflows of both cold and warm gas. And if you look at these things in, for example, molecular lines of like carbon monoxide, you see very high Mach number turbulent velocities. So the sort of prototypical starburst galaxy is M82. This is a nice composite image. What you see here in white are the stars from the galaxy. And then in sort of red or purple here, you can't see it very well with the light, but is an image, it's a filter around H alpha. So what you're seeing here is the warm ionized gas that's coming out in this biconical outflow. It's being launched from the center of the galaxy. And it's pretty clear at this point that this is being launched because there's a very rapid star formation going on in the center of this galaxy. So the question really for this talk is what drives these outflows and what drives these turbulence? And so this is an old question. Yeah?
Can you comment on whether the new supernova in M82 is going to tell us anything useful about outflows?
You know, so I just found out about this yesterday when I was doing a review of the material. So I actually don't know. I mean, it might. Obviously, if you see something in response to this, but I mean, it's not clear how quickly. I mean, maybe 10 years from now, but even that, it's not clear to me what it would do. But maybe you, since you might actually know better than me because you've thought about it. But
could you see anything like an absorption or something using the supernova light to tell you that?
You're guess it's as good as mine. Sorry. Yeah, I just, like I said, I just found out that there was even such a supernova. I guess it's the second closest supernova since, or first closest since 1987.
Yeah, yeah.
So this is one of the reasons that this is nice to study is it's relatively nearby. Okay, so getting back to the question, so this is a long-standing question, what drives these outflows and this turbulence? And so there's been lots of ideas proposed over the year. Sort of the most popular is that it's supernova-driven. So the supernova just dumps mechanical energy and heat the ISM, and that's enough to drive a wind if you have lots of these supernovae going off all at the same time. Stellar winds are another component. AGN, if they're present, will almost certainly do things to the interstellar medium. A popular idea more recently is the direct momentum input from photons emitted at stellar, emitted by the stars that are forming. The direct momentum impact, because they're absorbed by dust, can drive turbulence. That's the sort of focus of this talk. But also people have thought about cosmic rays and magnetic fields. I think for M82, the overwhelming evidence supports that it is actually mostly supernova-driven, although I think there are people who would claim that radiation plays an important role here as well. They don't make pretty pictures, but the other thing to keep in mind is in addition to these hot outflows, you have these very cool, cold neutral material, outflows of cold neutral material. And you see these not in images, but in spectroscopy. And you also see actually outflows of molecular material as well now. And actually most of the material that's being lost in these galaxies is coming out, or seems to be coming out, in this cold, in these cold clouds. And so the way you infer their presence is by spectroscopy, particularly the sodium 1D line is popular. These are absorption lines. It's a doublet, so here in black you see the rest frame doublet in this fit. This is a fit to a particular starburst from Crystal Martin. And then you see these two broad Gaussians that are fit, and you can see they're blue shifted from the rest frame. And they're blue shifted by quite a bit. So if you look at a sample of starbursts ranging from relatively low mass dwarf galaxies to ULERGs, you can see this is circular velocity down here, which is essentially the mass of the galaxy versus the blue shift. And you can see roughly that the blue shift seems to correlate with the mass. So that's consistent with this stuff being launched at near the escape velocity and being unbound material from the galaxy.
That's it.
What?
I mean, except for velocities below 200 kilometers a second, where there clearly is an offset. It looks sort of flat to me.
Yeah.
Good enough.
Well, details. It's even worse here, actually. So the star formation rate, you have the star formation rate versus the blue shift here. And again, if you kind of ignore that this is a lot of scatter up here, you can see that there's a pretty clear correlation between star formation rate and outflow velocities, which is what you'd expect if star formation feedback is driving these outflows. Okay, so a lot of what we want to do is try to explain these sorts of trends. Now I picked an old plot here, because I used this when I gave a talk in Maryland, so I wanted to show blue, but I think this has gotten better since 2005.
Is there a correlation between star formation rate and mass outflow rate?
What's that?
Can you show
It's harder to get a correlation between mass outflow rate because the mass outflow rates are much more uncertain than the velocities themselves. But it is, I think, I haven't ever seen a good plot of it. My understanding is that modulo the uncertainties in the mass outflow rates, there is a reasonably decent correlation between the outflow rates and the star formation rates. But again, the mass outflow rates are much more uncertain than the velocities. Because you see a sodium D line, you can measure a column, but turning that into an actual mass outflow rate, it requires a lot of assumptions that are kind of
These are also on the flat part of the curve of growth. So often.
Yeah, there's a lot of problems. Norm wrote an entire paper on this that you probably don't want to read. So the sources we're interested in are the ultraluminous infrared galaxies. These are sort of in the nearby universe, these are the highest star formation rate galaxies you can find. This is ARC-220, this is sort of the prototypical case. The main thing to note from this is that the spectrum peaks in the far infrared. This is about 100 microns. Even though most of this emission is assumed to be coming from young, massive stars which emit in the UV. So almost all of the emission is absorbed by dust and then re-radiated in the infrared in these galaxies. And that's important If you look at these sources in the optical, this is Hubble images, you see basically train wrecks. So the idea is that this phenomenon is driven by interactions, maybe major mergers. There's a lot going on here. And the way we get probed, the main way to probe the properties of these galaxies is through, in particular, the molecular gas in the galaxies, is through the molecular lines. So you have emission lines like carbon monoxide 2-to-1 transition. And you can make maps of these galaxies. This is a map of R220. You can get velocity dispersions. The velocity dispersions are quite high. Mach numbers of 50 are common in these galaxies. You can use this to probe densities and temperatures if you have enough molecular lines available. And as ALMA comes online, this is just getting better and better, so we should have more and more information about these sources. Right now, we have enough information that theorists can kind of play around with their models, but I think we'll actually be able to constrain things better in the near future. Okay, so the main focus of this talk is the role of radiation forces. This idea has been around before Norm and company wrote this paper in 2005, but I think it's fair to say that this paper has had the most influence recently. And so those guys and numerous other people and collaborators of theirs have basically argued that momentum injection from radiation pressure on dust grains is actually the primary driver of this turbulence in these outflows and ULERGs, maybe even starbursts, and they may also even be responsible for driving the disruption of GMCs in our galaxy. I think all these statements are at least a little bit controversial. Norm isn't here to defend them, but I'm sure he would if he was. I think it's at least a plausible argument that radiation is playing some role, and I think it's worth exploring this possibility.
What's the difference in definition between a starburst and a ULERG? Is a ULERG just a close starburst galaxy?
Well, ULERGs, they're all kind of, ULERG could, I guess, I don't know, I think a ULERG would almost fall under the category of a starburst. A starburst is kind of, I think, a poorly defined term. I think starburst usually refers to things like dwarf galaxies that are forming stars at like 3 to 10 solar masses per year. And ULERG usually refers to something which is much bigger, like R220. It's forming stars at a much higher rate. It's basically, the ULERG, of course, is a reference to the infrared luminosity, which may or may not be as big in a starburst, a smaller dwarf galaxy. Because the radiation, not all of the radiation gets absorbed in these lower mass galaxies by dust. Okay, so then,
because we don't have much dust? Sorry.
I think they're just not as dense, is the main difference. I'm a little shaky on all these observational things. This is a new area for me, but I think that's the right, I think what I said was correct. Okay, so the basic prescription they use to estimate the amount of feedback is the momentum injected, or the momentum per unit time injected into the interstellar medium from these young stars. And so this should scale roughly as the luminosity divided by c, because this is sort of the momentum budget you have in the stars. Now, if you just had ultraviolet absorption of dust, this factor out in front would just be unity. Basically, every photon would go out, it would get absorbed by a dust grain, and it would impart its momentum, and that's all you get. Because the momentum would be downgraded, the energy that you absorb would be downgraded to infrared and re-radiated. Now, if you have an optically thick, if your galaxy is optically thick to the infrared, you can get this additional factor of tau IR, and which can be quite large if the infrared optical depth is large. And what's happening here is you're getting multiple scatterings or multiple emissions and reabsorptions, and this allows you to increase the forcing you get for a given amount of luminosity. Okay? So if this factor is here, you can make feedback much more efficient. And this is why I'm focusing on ULERGs, because it is the case in ULERGs that you kind of expect this tau can be of order unity or larger. Okay? So you can sort of, go beyond analytic models, if you will, by looking at numerical simulations. So people have done SPH numerical simulations, in particular Phil Hopkins and collaborators, which includes Norm, have done a lot of work on this. They've put in this sort of momentum feedback prescription into their models, and they've shown that actually with this prescription they can do a pretty good job of reproducing wind velocities, outflow rates, and things like that, turbulent velocities that are inferred. But they need radiation feedback. If they do the simulation without radiation And basically this prescription is just what I said here. The only thing they did was they added this little efficiency factor as a kind of kludge. And they were thinking, well, you know, these things are clumpy, and so radiation and gas are not going to be perfectly coupled. The radiation is going to seep out through these low-density channels, and that will reduce this, this coupling a little bit. And they said, oh, well, this efficiency is maybe a half or 1/3, and they put that into their prescriptions. Now, this basic idea has been challenged recently by Mark Krumholtz and Todd Thompson. And what Mark and Todd did was they did some numerical experiments, or some numerical simulations to test and see whether this assumption should work. And so what they claim is that because of something called the Rayleigh-Taylor instability, which I'll describe shortly, this instability allows you to open low-density channels in the flow through which most of the photons seep out, and that the actual coupling you get is much lower. In fact, this eta is much, much less than 1 in practice. And so your momentum rate, that injection rate, is basically going to be limited to L over C, roughly the momentum you get just from direct absorption of dust of the UV light by the dust. Okay? So basically the question for this talk is who is correct? Okay? So before I get to the simulations, I just want to take some time to describe our numerical method and some applications. I'll go through this relatively quickly. So I'm going to throw up some equations here, but details aren't so much important as the basic overall idea of what we're doing. So if you want to solve radiation transfer, you actually have to start with the rate of transfer equation. Okay, and the static version of this equation is shown in white. And I've included scattering here, so and then because we're solving this in simulations, we have to include velocity-dependent terms as well. You get these by doing Lorentz transformations to the fluid frame and expanding to V over C. And one thing to note about this equation is this intensity depends on both the space coordinates, position space. It also depends on 3 momentum coordinates, which we usually think of as the photon frequency and the photon direction, or the direction on the sky, which is defined by this unit vector n hat. So this is a 6-dimensional time-dependent quantity. Okay, so solving this is generally a hard problem. It's made worse when you have scattering present because your source term includes integrals over angles and frequencies of this intensity. So you have an integral differential equation, which generally needs to be solved iteratively. So this is a very expensive calculation to do. So we normally don't want to do this. So what's typically done is you reduce the complexity by integrating over your momentum space variables. Now I should have noted that this equation is for gray opacity. We've essentially integrated out the frequency already. It's even much worse when you include frequency dependence in here. And for the sake of this talk, we're just going to assume gray opacity in what follows. But adding the frequency dependence back in is not conceptually difficult.
But in principle, you still separate UV with re-radiators.
I'll get to that when we do the simulations. We actually ignore the UV for the sake of the simulations here. That's the next thing to do, though, is to include both. So what you do is you integrate over angle and you integrate over frequency, and you get the radiation energy equation. You just integrate this over frequency and angle. You can also multiply this whole thing by one of these unit vectors, these n hats, and then integrate over angle, and you get the radiation momentum equation. And again, you have these complicated source terms. The precise form isn't important. What I want you to note, though, is that you have the time derivative of an energy density plus the divergence of the flux equals some source term. And the nice thing about this is these are flux conservative equations. This is a very common occurrence in physics. We see this in hydrodynamics. So there's a lot of machinery built up to solve these equations, so we can make use of that. The only problem is that we have this radiation pressure tensor in here, and we don't know how to calculate that. We could, of course, go to a higher order moment and get a time-dependent evolution equation for this, but we have an even higher order moment appearing in the equation. So typically what we have to do is we have to stop at the momentum equation and make some prescription for the radiation pressure. And the real question is, how do we handle that? So the simplest thing to do is just replace it. You define an Eddington tensor, which is just the ratio of the radiation pressure to the energy density, and put F times E in this equation. That hasn't gotten you anything because you still need to specify the Eddington tensor. But this is a nicer quantity to work with because it just depends on the angular distribution of the radiation field. So when you put these radiation moment equations with the hydro equations, you get the sort of full set of equations we're solving. I've shown the hydro equations in white, conservation of mass, momentum, and energy. Radiation in yellow. These are just those complicated, ugly source terms. I've just simplified them. The key thing to note is that the negative of these source terms come in on the right-hand side of the hydro equations because total energy and momentum is conserved. And this turns out to be a very hard system to evolve. Basically, the issue is that the dynamics you're interested in occurs on this sound crossing time, or if you have MHD, maybe the Alfvén crossing time. And that's usually very long compared to the light crossing time in which these equations evolve. So you have to solve these implicitly. And these source terms can be very stiff, so coupling them to the hydro can be very difficult as well. And so in fact, this took two Princeton grad students' thesis projects. One to figure out how to do it in 1D, and then my collaborator, Jan Fay, spent his thesis implementing it in 3D. So even after you've done that, you still have this issue of what to do with the Eddington tensor. And so that was my contribution to the project, was coming up with a scheme for computing that. Now before I tell you what we do, I want to talk about what other people do. And this is actually what Mark and most importantly, this is what Mark and Todd did in their calculations. They used something called the flux limit diffusion approximation. And so what you do is you just throw out the momentum equation for the radiation field entirely, and you replace it by this prescription for flux. There's this function called the flux limiter in here, but if you ignore this function, you just set it to 1, this is just the diffusion limit for radiation. The flux is determined by the gradient in the energy density. Now all this limiter does is it's a function, a local function of the energy density and the opacities. And depending on the ratio of these things to the gradient of the energy density, this function, if it's in the optically thick limit, it just goes to unity. Now if it's in the optically thin limit, all it does is make sure that the flux doesn't get larger than c times E. So this is the causal limit. You can't have the flux being any bigger than c times the energy density. And that's all this thing really does, is it sort of makes sure you go between these two limits. Now it's important to note that this isn't even necessarily the general correct optically thin limit. This is only right for if you're infinitely far from a point source, but that's, I guess, just a detail. So the issue here is that you've replaced your 4 PDEs with 1 partial differential equation, which makes things a lot simpler. But of course, you've thrown away a lot of in principle, important information. One thing is that this limiter is only a function of local values. So you've ignored the non-local aspects of the radiation field. And the flux is always required to point along the gradient of the energy density, okay? Which in general is not the case in radiation.
Basically, if I have a cloud which is half hot and half cold, it streams along that way instead of just the wave, and that exactly that.
I'll show you a nice example of what this does shortly. Okay, so our method, which I'll describe briefly, is something we call the variable Eddington tensor method. So we don't throw away the momentum equation, we keep it, and what we do is we compute this Eddington tensor on every time step using a time-independent solution of the radiation transfer equation. And this is usually a good approximation because we're looking at non-relativistic flows where the light crossing time is fairly short. And where it's not short, the Eddington, the diffusion approximation usually holds to pretty high accuracy. And so what we solve is the gradient of the intensity along a particular direction, which we have to specify, is just equal to some source term minus a sink term. Now this looks a lot simpler compared to what I showed you previously, which even with the time derivative dropped off, was this big complicated expression. And basically all I've done is I've absorbed all of this into my definition of chi and my definition of S. But this is something that has an analytic solution if we know S. And we can use that to solve this equation numerically everywhere in our code, or everywhere in our simulation domain. We just need to set up a array of a grid of rays, and a spatial grid, where we can compute these intensities, emissivities, opacities. Okay?
So the fact that you use the short characteristic means that you're slightly more diffusive than I guess you should be, but much better than the
Much more efficient. Yes,
Yeah.
yes, that's the idea. I'll show you, I'll say more about this shortly. Just to note that because I've absorbed all this complexity of the S into S, you have to keep in mind that S can depend on the intensity and moments of the intensity. So So when that's true, for example, whenever you have scattering. And in that case, we have to iterate this equation, which can be expensive. But the nice thing is because we solve this every time step, we usually have a very good approximation for this intensity, or for the intensity from the previous time step. So this usually converges quickly. And if it's thermal, in principle, we don't need to iterate at all. This is just the Planck function. But oftentimes we have to iterate, even in that case, just because of our boundary conditions. So we need to set up an angular grid at every point in our simulation. This is actually pretty well known how to do. People have been doing it since the early 60s when they got really interested in Boltzmann transport of neutrons because of atomic bombs. So most of the literature goes back to then. So we didn't have to do anything new. We basically divide our unit sphere up into 8 octants, and we distribute the rays equivalently in each octant. And this is nice because, for example, if your radiation field is isotropic, your fluxes naturally cancel, et cetera, et cetera. So what we do is we specify some distribution in each octant. The simplest thing is 1 ray per octant. You choose this angle correctly, you get back the Eddington approximation. If you want to do better than Eddington, you need to do at least 3 rays per octant, so on and so forth. We usually do 10 rays per octant, so 80 rays total for our 3D calculations. We think that's good for most of the problems we're interested in. Now, how do we use this? Well, at each point in our grid, we define some intensities. And so what we do, if we want to calculate the intensity at 1, which is sort of the center of our grid zone in our hydrogrid, what we do is for this particular choice of ray, we just extrapolate back to where it intersects this grid, and then we interpolate the intensities on these neighboring grid zones. So at some point, at some place, we need the incoming intensity specified by some boundary condition. But then we can integrate using this time-independent radiation transfer equation along this ray to get the intensity at 1. We just need to know the source function, which we can interpolate from the neighboring grid zones. Okay, and then we just sweep through the grid. These points are ordered because we have to sweep through the grid in a particular order because, for example, if we want to calculate the intensity at 4, we trace back here, and then we need to interpolate on these intensities. We already need to have calculated the intensity at point 1.
But you also have to go, oh, I guess, sure.
Yeah, and so if we're going backwards, we have to go the other way. So we always sort of move away from the corners, if you will. And this is easy to do in Cartesian. It's a little bit more of a pain in spherical or cylindrical. But the key thing is, as we go along, we're basically tabulating quantities like the energy density, the flux, and the radiation pressure tensor. And so what we do is we just basically tabulate these quantities, and at the end of the day, from this calculation, we take the ratio of the pressure tensor to the energy density. That gives us our estimate for F. And it's a pretty good approximation because all we've ignored is the time dependence. But we're keeping that time dependence in our radiation, our moment equation.
So why is it still important to even have the F? Because you have actually calculated the PR now.
What? Sorry.
Since you have the radiation pressure, why do you still?
Well, it's a little bit better because we want the energy density. We want the radiation moment equations to evolve their own energy density, and we actually have played around with this, and it is better to just use the F.
Are you constrained in any way by the direction radiation is diffusing?
In the way it's diffusing?
In other words, things are upwind or downwind.
Not for this type of calculation. We've done another global we implemented a time-dependent code, time-dependent rate of transfer code, which is. But the nice thing about this is because we dropped the time derivative, it's basically it's not an elliptical, but it's almost like an elliptical equation, and so we don't have to worry about these sorts of things.
Can you just explain if you will, compared to this diffusion method equation, what's the difference between your treatment and that? I mean, like what's the difference that you are,
We solved the rate of transfer equation.
which is diffusion moment,
What's that?
which is related to diffusion equation.
No. So we're solving this angle by angle. There's no diffusion approximation in the rate of transfer equation. The radiation transfer equation with time dependence is just the full Boltzmann. It's equivalent to the Boltzmann equation for photons. The only approximation we've done is for most of these calculations, we've done gray opacity, so we're ignoring frequency dependence, and we've dropped the time derivative. But all of this basically as we propagate across the grid, we have the radiation field at one point is very sensitive. Radiation field here can be very sensitive to what's going on down here. Whereas in the diffusion approximation, you only really care about the local gradients in the energy density. So there's a lot more information here. And I'll try to maybe explain that more with some of the next couple slides. Okay. So what we do, I'm getting a bit behind here, so I have to hurry. On each time step, we solve the equations of the hydrodynamics or magnetohydrodynamics using the standard Athena algorithms. Okay, that gives us a temperature and density distribution. With that temperature and density distribution, we can solve the time-independent radiative transfer equation, like I just described, to get this Eddington tensor. And we take that Eddington tensor and then stick it into our time-dependent evolution of the radiation energy and momentum equations. Okay, so these equations are still time-dependent, even though our Eddington tensor is estimated from a time-independent calculation. And then when we calculate this, we get our estimate for the radiation source terms, which we put back on the right-hand side of the hydro equations, and we sort of close the loop. So we just iterate this over and over again each time step. All right, so I want to give you a couple. Okay, so before I get into this, I should just note, you're probably thinking this sounds horribly expensive if you're paying attention. And it is more expensive than doing, for example, flux-limited diffusion, but perhaps not as bad as you think. So I'm going to show you a comparison of flux-limited diffusion and VET calculations later in the talk. And the VET calculations are about a factor of 2 to 3 times more expensive than the FLD computations. So that's not negligible, but it's the difference, as I'll show you, it's the difference between getting the right answer and getting the wrong answer. So I think
partitioning between the hydro bars and radiation.
well, so it depends. So this is the thing. For the FLD, roughly speaking, it's comparable in cost to the hydro. And for this particular problem, the VET is about 3 times as much as, well, a little more than 3 times as much as the hydro. And so when you put it all together, it's about, I maybe did that wrong, but it's about 2.5 times more expensive to do the FL.
Isn't it amazing considering you've got 80 suits to do for the radiation and only like 3 for the hydro?
The problem is that when we do it, I can kind of tell you. This is getting me a little bit farther afield, but the issue is that we solve this implicitly, right? And so the main advantage is this for various reasons, this system, we also solve, when you solve FLD, you also solve the energy equation implicitly. And that tends to converge slower than this solve because of the way FLD works. There's a sort of non-linear aspect to FLD that makes it somewhat more expensive. And so that kind of compensates for the fact that we have to do this additional short characteristics calculation. It's possible we've just implemented our FLD in an inefficient manner, but compared to other FLD calculations out there, we don't seem to be doing much worse. So, okay. So what I want to show you here is results from a cloud and radiation calculation. This is a bit of a toy problem, but we actually did some science with it, which you can look up in Kroga et al. 2014 if you want. But so this is a calculation with our VET, and basically we have a cold, dense cloud surrounded by a low-density interstellar medium and radiation field coming in on the left here. And so this shows the radiation energy density returned by the code. In the cloud itself, it's nearly 0. Outside the cloud, it's basically just constant because we have a constant flux coming through, and it's more or less horizontally directed. Behind the cloud, it's very low energy density. It's not 0 because there's scattering opacity here, which is scattering light into this region. But you can see you get a well-formed shadow from the VET calculation, which is what you expect. Now, you can imagine that this is a whopping big gradient in the energy density, right? And I said for flux-limited diffusion, wherever there's a gradient in the energy density, there's a flux. So flux-limited diffusion sees this, it says, oh, I want to fill this in, okay? And so if you actually look at an FLD calculation, if you evolve it very slowly so that you actually watch the radiation field come across the cloud, you actually see that it just diffuses around the cloud. And if I ran, that's the last still I have, but if you run further, it's just basically just as hot on the front side as the back side. This is a well-known problem with this technique. Okay. I'm a bit behind where I want to be. I guess I'll just go through this real quick. So I just wanted to show, so that was kind of a toy problem. I wanted to show that this can be important in a real astrophysical problem. And I just want to note, I don't really have time to get into the science of this, but we have been using this to do 3D calculations in accretion disks. So mostly what we've been doing is local simulations where we zoom in on a small patch of the disk, and these are so-called shearing box simulations. We're just doing a Cartesian simulation. But I would like to note we are now doing global radiation hydro simulations. This is a snapshot from one of our simulations. Jan Fay, my collaborator, is doing this. And this is actually an Eddington ratio of 0.1, which is pretty amazing to me. But anyway, what we've done to a lot so far is these local simulations, which we can do at higher resolution. And basically what you do is you have your x-coordinate as your radial direction, your y-coordinate is your azimuthal direction, and z is your sort of height above the midplane. You have tidal gravities, which points downward in the top half and upward in the bottom half. And so this shows the log of density. And the thing that's special about these shearing boxes, well, they're periodic in the azimuthal direction, and they're shearing periodic in the radial direction. And that means if a fluid element comes through the outside, it gets put back on the inside. It gets shifted in position and velocity by an amount that's proportional to the local shear rate in the disk. Okay, and there's also a Coriolis force. And so this allows something called the magnetorotational instability to amplify magnetic field and drive turbulence. And so I just want to show you a simulation, one of these shearing box simulations. I'm not going to go into the science because I don't have time. But I think this demonstrates some of the power of our VET method and how it differs from things like flux and diffusion. So this is a very thin simulation. We generally run thicker simulations, but we were reproducing some earlier results. And they did, for various reasons, did these very narrow boxes. So I'm only showing you the top half of the simulation. And what I'm showing you is the intensity that we're calculating on every time step in our simulation. And we're doing this for 80 different directions. And this particular, what you're seeing is the view normal corresponds to the angle for this particular intensity. So we're actually looking a little bit down on the disk. And so because it's so thin, this upper region is optically thin. And I'll run it, this movie runs for about 8 orbits. And one thing to note is the radiation field is shearing periodic. Maybe can we turn off the lights real quick? It's shearing periodic. So you see it's a little hard to see in here, but you see this pattern moving across here? It looks much better on my screen. What you're actually seeing is you're seeing through the box, and you're seeing the sheared periodic copies of the box in the radiative transfer. Okay? And as this dynamics moves on, the photosphere moves up, and you start to see these dense filaments. These are filaments of high-density material driven by Parker instability and MHD turbulence, and you can see them shadowing the background radiation field. And I guess the main thing I want you to take away is this is a very non-local radiation field above the surface of the photosphere.